Okay, so today what you're going to do is take notes on how to calculate equilibrium constants. By this point, you should have a pretty good understanding of what chemical equilibrium means and also how Le Chatelier's principle applies towards chemical equilibrium. So, chemical equilibrium constants. So, equilibrium constants. So the equilibrium constant is abbreviated with the unit KEQ, and it is the ratio of product to reactant concentrations. So remember, concentration in chemistry is molarity. Remember, molarity is moles per liter. When we are calculating the equilibrium constant, we raise the substance to the power of the coefficient that comes before it in a balanced chemical equation. We'll go through examples of what this means. Um, how to determine what is included in an equilibrium constant expression is based on the state of matter that it is. So liquids or solids, okay, are not included in equilibrium constant expressions. They are not involved. So the equilibrium constant expression. So here's just a generic chemical equation that we could apply towards anything in chemistry. The equilibrium constant expression would look like this. The concentration of the products raised to the coefficient multiplied by each other over the concentration of the reactants raised to their power coefficient. So when writing equilibrium constants, a couple of things you need to know. Only gases and aqueous solutions are included in equilibrium constant expressions. The reason is gases take up a lot of space, and their concentration can change depending on the amount of space that they take up. And aqueous solutions, think about saturation. You can add more solid to increase the saturation of the solutions. You're therefore changing the molarity or concentration, or you could dissolve less. So equilibrium can change with gases and aqueous solutions because of how their concentrations can change. Solids and liquids, their concentration is based on their density, and their density can't change, and because their density can't change, the equilibrium of them doesn't change within the expression. Let's go through an example. So we want to solve for the KEQ, or the equilibrium constant, for the following reactions. Okay, so we have these first two reactions. Reaction A is nitrogen reacting with hydrogen to produce ammonia. It's a reversible reaction, goes in both ways. All states of matter for the first reaction are gases, so make sure you're paying attention to the states of matter that are listed. Reaction number two, we have barium sulfate decomposing into barium ions and sulfate ions. Barium sulfate is a solid, where the ions that are produced are both aqueous. So pay attention, it's the states of matter. So for reaction number one, the equilibrium constant, okay, would look like this. All aspects of the reaction are included because all states of matter are applicable with the rules of equilibrium constants. So the concentration of ammonia raised to the second power over the concentrations of hydrogen and nitrogen. And hydrogen would be raised to the third power because the coefficient in front of hydrogen is a 3. For the second equation, pay close attention. It is just the concentration of barium times the concentration of sulfate. Barium sulfate is not included in the denominator because it is a solid. Now that does not mean that the denominator becomes a 0. Okay, it's just not included, so it's not going to impact how the equilibrium expression is written. So with equilibrium constants, the whole purpose of solving for these tells you whether the reaction is going to favor the products over the reactants and which way it's going to tend to flow and have the equilibrium go. So if KEQ is greater than 1, we're going to be favoring our products. Where if it is less than 1, the reactants are going to be the ones that are favored. So now we're going to actually solve for an equilibrium constant. So we have our made-up equation, and they're telling us that the KEQ for this equation is 0.65. Okay, so first thing we're going to do is we're going to write the equilibrium constant expression for the reaction. Okay, and it would look like this. We could assume that all of these states of matter are either gases or aqueous solutions. So it would be the concentration of A times the concentration of B over the concentration of AB raised to the second power. And they told us in our given information that the KEQ in this part was 0.65. Okay, so this is less than 1, okay, not greater than 1. So keep that in mind and what that means, whether it's reactants or products that are going to be favored. Part B is giving us some additional information. It's saying if the equilibrium concentration of AB is 2 molar and the equilibrium concentration of A is 0.5 molar, it wants us to determine what the equilibrium concentration would be of B. So now this just becomes a math problem. All you have to do is plug in the numbers, rearrange the equation, and solve. So 0.65 is equal to 0.5 times B over 2 squared. Everyone here should be fully capable of rearranging this equation to get the proper answer. And by doing so, you get the concentration of B to be 5.2 molar. So another example, we want to calculate the KEQ for the following reaction. So they're giving us the concentrations of the different things that are present within the reaction. Our chemical equation looks like this. Once again, unless it's specifically stated, you can assume that all aspects of the equation are included in the equilibrium constant. So the equilibrium constant would be PCl3 times Cl2 over PCl5. And then you just plug in your numbers and get your answer. We get a very large number here, 31, much greater than the number 1. So in this case, the products would definitely be favored over the reactants. And that is it.